Okay, ready, set, go.
So this talk is about a paper in RIPS 2020, was presented, named Generalized Independent Noise Condition for Estimating Latent Variables in Causal Graphs. And basically what we want to do is we want to identify the causal graph of observable and latent variables by first identify the clusters of observable variables based on their latent variables. And then we want to identify the causal order of these latent variables, which is a novel thing. And like as mentioned in the paper, the previous methods were only capable to uh, work with observable variables. So as I said, uh, this is the case that we want to work with latent variables as well as observable variables, which is the significance of this paper. And so here's the model of this paper. We have a set of variable V, which is consistent of X and L, the observable X and latent L's. And they also consider that the variables are generated using this process, which basically says that each variable is a cause of its earlier variables in causal sense, plus non-Gaussian noise term.
Well, I want to comment on this
Question.
last one. I don't know, I didn't read far enough, sorry, to know the reason why they made this confusing notation. All they mean is that it's a DAG, directed acyclic graph. That's it. Like there are no loops basically. So and you can have some kind of a topological sort order. That's it.
Does this capture simultaneous causes as well, or are they necessarily ordered?
No. So later I'll get to this, but they assume that there are no direct causes between the observable variables. So it's only the latent variables that causes the observable variables.
But I think
I'm asking a different question. Yeah.
There is no time. There is no time here.
No time.
It's just samples. So there is no time order. The order is causal. Because of a DAG, is like you can always start with some variable and get downstream to the descendants, but the condition there is that from descendants you cannot get back.
But even if you have a DAG, can't you have two nodes in the DAG that have an arrow to some other observed node? That's what I'm asking. So simultaneous cause, right? Where you have.
Oh well, then Sajad has answered your question. He'll get to.
Yeah. So basically, I think they for example, one variable I think could in theory have two latent causes, but not directly. Like so, one of them causes the other latent. So
so you can only have one parent, right?
Yeah, all the examples in the paper has only one latent parent. So here is the basic problem definition. We have a set of x's variables that are observable. We have their values. They could be anything. Like it could be the answers to some psychological question, or they could be stock market prices, anything. And we want to identify the L variables, which are the latent causes of them, and they're also the orders of them.
Well, can you go back to that graph? Because I think this also answers my question. So they do allow for multiple causes between latent variables, right? So L1 and L2 in this graph affect L3. L1 and L2 affect L4, but but not for observed variables, it looks like.
I don't see a condition that prevents multiple latent variables causing the same observed variables either. The graph doesn't list it, but I don't see a condition on that.
Yeah, that's all I was wondering. Looks like it probably is allowed.
Yeah. Okay, so basically this paper builds on previous existing works, and it was called independent noise, which is the condition between the set of variables z and y, that if the condition is that if y minus some weight variable z is is independent from Z. So if we can find such weight matrix, we can say that these are Z and Y are independent. And the cause of that is that if we uh, identify the wrong causal relation in a graph, this condition will be violated. So here we can see that x2 is causally earlier than x3, and x2 is causally earlier than x1 and x4. So we can say that x2 is a root cause. So in previous methods, they use this kind of this independent noise condition to identify the whole causal relation of the graph. Uh, but as I said before, this is the case where we don't have latent variables. So here in this paper, they consider a case called a linear non-Gaussian latent variable causal model, which has 4 assumptions. First one is that no observable variable is earlier than a latent variable. Second assumption is that the noise terms are non-Gaussian. Third assumption is that each latent set of variables has at least double their their members observable variables. So here, for example, L2 and L1 are a group or a set of latent variables, and they have 4 observable variables. And the last assumption is that there are no direct edges between observed variables. So if we want to apply the independent noise condition on this graph, for example, where we have latent variables, this will basically be violated everywhere because we have confounders. But if we had access to the latent variables, we could write, for example, here we could write x1, x2, x3 in terms of L1, L2, and some noise conditions, noise terms. And because this A matrix is 2 by 3 by 2, we can always find a W that if we multiply it in this cross covariance term between Y and L1, L2, it could be 0. And if that's 0, then the Y vector will essentially be a W times the noises, which is independent from L.
Well, but this is ICA, right? This is just ICA, independent component analysis. We can run ICA.
Yeah, but the point is that we don't have access to L1, L2. So if we had that, we could just go with the ICA and do that. But since we don't have that, we have to use something called, they used here called something called surrogate variables. The Z set here, X4 and X6. And they show that we can use these surrogate variables instead of direct parents. So here, for example, they rewrite the L1, L2, and L3 based on their earlier parents. And they see that if we have this specific W, then the residual of Wy minus Z is independent from Z. And so what was I saying? Yeah, so basically, intuitively, they were saying that if you have Y relative to Z is independent of Z, although x1, x2, x3 are generated while L1 and L2, which are not measurable, Y relative to Z is as a linear combination of Y removes the influence of L1 and L2 by using the Z as a surrogate variable. So formal description of the gene condition, the generalized independent noise condition, is that let Z and Y be 2 sets of variables. Z and Y satisfy the gene condition if there is a non-zero weight vector such that the linear combination of y is independent from z. And this also has a, roughly speaking, has a graphical implication, which means that if y and z are deseparated by the latent common causes, and then they satisfy the gene condition. So here, x1, x2, x3, and x4, x6 are deseparated by L1, L2, so they do satisfy the gene condition. Whereas this case, x1, x2, x5, and x4, x6 are not deseparated by L1, L2, so they don't satisfy the gene condition. Similarly, we have this for this case, x7, x8, and x6, which satisfy the gene condition, and this one does not satisfy the gene condition. Okay, so given this basic theory on gene, they came up with an algorithm to identify the whole causal graph of the variables. And this basically is that in the first step, they find the clusters of observable variables that share the same parent immediately. And then they determine the causal order of this latent variable. Okay, in the first step, I don't think I have any choice but to read this theorem, but so the theorem, the paper says that let X be the set of all the observable variables in the linear non-Gaussian model and Y be a proper subset of X. So if X excluded Y and Y follows the gene condition and there is no such a subset as Y prime, blah, blah, then Y is a causal cluster. And the dimension of the latent parent is the dimension of the set y minus 1. So for example, here, we can see that x5 and x6 and the corresponding y subset, x1, x4, x5, and x8, satisfy the gene condition. So x5 and x6 is a causal cluster. But for x1 and x2, x5, this doesn't satisfy the gene condition, so it's not a causal cluster. So this is the algorithm to...
Can you rewind, can you go slow? What do they mean by dimension? What is L of Y? What is
dimension of Y is the number of elements in Y, which is 5 and 6, which is 2.
What is L of a set? L of 5 and 6.
L of Y is the dimension of L of Y is the number of the latent parents. So here x5 and x6, the dimension of Y is 2, and the dimension of their latent parent is dimension of Y minus 1, which is 2.
How do they identify it without the graph?
Sorry, come again?
How do they identify it without the graph? So like with graph, we can see that, but what are they claiming? Like, I don't know how L of Y is computed because it could have had 2 parents or something, right? Like there could be L5 that is a parent of X5 and X6 as well, right? So do they mean like the minimum possible or something like that?
I'm not sure, but first of all, the dimension of Y is, we choose it. We choose the variable.
Well, we don't know the graph, right?
Yeah.
Like it could be this as well. Like add this to the graph that you already have, and this will be L5. So why are we saying it's 1?
I think because of the assumption that they had, that they said each set of latent variables had at least twice their size the number of observable variable. So here, for example, if you have x5 and x6, they can't have two direct latent parents because that will violate the assumption.
Okay, okay.
Something like that.
Thanks.
Okay. 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 So here's the algorithm that. So they first choose some variables and they check if they're a cluster, and they find the different clusters, and if these clusters have some overlaps, they will merge them into a new cluster, and they will continue this process until all the variables are assigned to a cluster. And so, and you have an example here based on the graph. And the last part is the learning the causal order of the latent variables. So, for example, so they have a lemma here that they say if you choose two clusters of the observable variables, if and also based on the assumption, we know that the number of the observable variables is at least twice the number of latent variables. So we say that if half of the variables in one cluster satisfy the gene condition with the rest of that half and the other cluster, it means that the first one, the latent root of the first one is a root. For example, here, what I meant is that for x5, x6, and x7, x8, if we set if we set SR the set of x5 and x6 and sk the set of x7 and x8, we can see that if x6 sorry, if it's if x5 satisfy the gene condition with x6, 7, and 8, it means that the L3 is causally earlier than L4. And so it's not, so this is another example of that too. And here's a algorithm, formal algorithm for that. So they basically start with empty sets and they iteratively build this causal relation based on this proposition 4. And so they did some simulations on their papers, and basically their experiments is twofold. First one, they experiment on a set of synthetic data, which in this case they have 4 different DAG structures, and each case 1, 2, 3, 4, it gets complicated as it goes on, and they measured the performance and compared it with the previous methods based on the relative number of errors that they made in estimating the relation. And by that, I mean finding the causal relations, because they have 2 tasks basically here. The first one is to find the causal cluster, and the second one is to discover the latent variable orders. But the previous methods are not capable of doing the second order. So here they are just comparing with the first task. And we can, as you can see, this method outperforms the other existing methods almost always. And finally, here's a real-world application of this. So here's a study to understand the impact of environment and personality on teachers' performance. And they formulated this as a graph, and they ran this their method on this, and they found that the result was pretty consistent with what psychologists experts have uh, hypothesized. So it's very interesting to see that, for example, they found the causal relation as in first first uh, first root cause is the if the teachers have role conflict, this will causes the classroom conflict, and this will affect their peer support, and that will affect the self-esteem, and finally it will affect the personal accomplishment, which makes perfect sense and is consistent with the what experts have hypothesized. And that's it. Any questions?
I want to rewind and start again and like go through this like 3 more times or 1 time slow. That was too quick. I don't know. So what was the complexity? Do you know how fast it runs? Why they're talking about pixels, right? Like with pixels or voxels, of course, we know those are just like they are like that. They are conditionally independent. There is something underneath that regulates the process that we measure. It's not the pixel of a cat causes the pixel of a mouse to run away. It's the latent cat and mouse, for example, if we have a camera. But we need to operate on a megapixel scale for that to work. So I wonder, can this work on a megapixel scale, or it's just too slow?
So what they said on the paper was just the case, this 4 case, and the most complicated one was this picture actually. So this one is the case 4. So I'm not sure if they can actually support large number of variables. So let's on the paper itself, they have a comparison between LSTC, and I don't see any comparison in terms of the speed, but basically they said that they were able to fully uh, identify the causal relation, whereas the other one couldn't when the graph was too complicated. But they didn't specify what they mean by too complicated.
They have to do a lot of comparisons, right, between different types of clusters to identify which cluster is like satisfies the gin between another set of variables, right? Like
so they have to look at the superset.
Right, I'm thinking about like there's this you're looking at the gin condition between two sets of variables y and z, right? They have to check like a lot of different combinations of variables in y and a lot of different like it's almost like a brute force. So it almost sounds like, I don't know if that's actually how they do it, but it sounds like until you found the gin, you can you know the cluster, but it could be on the last like steps.
Well, I forgot what the algorithm name was before PC, but there were like the algorithm preceding PC was doing just that. But PC algorithm was like does conditioning kind of successively. First condition on sets of 1, and then they will prune the results will prune some of the possibilities, then condition on sets of 2, and then you keep pruning, and so like you almost never like go to all of the set sizes and things like that. Like maybe
right, exactly.
And they sure know about, about PC algorithm. One of the authors, not in the name of the algorithms, but anyways, one of the authors is co-author of this paper, but I wonder. So it's not terribly efficient.
I can imagine, like for example, if you do this for, let's say, structural volume, you have about 70,000 voxels, and then it becomes very slow, very quickly, right? Or not?
Oh, can it be made efficient? I wonder. Yeah. So like when they do the surrogate variables, they're searching for something like an ICA, like a linear transformation that makes the variables conditionally independent. Right, Sajad? I don't know.
Sorry, could you come again, please?
When they build surrogate variables from clusters, they are running ICA on each of the combinations, like trying to find linear transformation, making them independent. Like, yeah, this examples with animation went so fast, I couldn't understand what's going on. Sorry.
Here, this was just, I was just showing the what satisfies the gene condition and what does not.
Yeah, so how is Z constructed? Is it X and Y concatenated or added, or
I don't want
like,
I don't know what you mean, but
what is the dimension of Z and Y?
What
3
do you
and
mean,
2,
like
2 and 3?
in this case, yeah, for what under algorithm that they had, so they pick all the possible combinations and see which one holds the
I'm
gene
just trying to
condition.
figure out what is the surrogate variable. So you have two here, Z and Y. So Y is a vector of 3 elements, X1, X2, X3, and Z is a vector of 2 elements, right?
Yeah.
Oh, so,
in
okay,
this
so
case,
you're solving, you've got to solve, and W is a vector, or, yeah, is a vector, okay.
The weight vector.
Yeah, so you have to do every combination, right, of sets between Z and Y. That's what I was talking about in terms of complexity.
Oh, no, I'm not worried about that yet. I'm just, okay, you have one combination. What you do with it, I don't get it. Like, you know, I need a simple thing, like I'm not philosophizing or anything. Like, I just don't understand anything. So what is W? W is a vector of 3 elements, right? No, it is a matrix of 2 by 3.
I think it's a vector that
you're solving rank reduced ICA basically. It's not square, right? It's so how do they do that? Like W is not invertible, but it's a matrix.
You know, I think because of their assumptions, this cross correlation matrix will always not be full rank, so it will always have a null space. So they can always find such W matrix that zeros it. And I don't think I think what they are interested in here is not to find the specific W, but they want to find if this set of variables holds the gene condition. So we just want.
But you have to. It's kind of EM-ish, right? You need to find W, or try to find W, and if you can't find W, for which
then they're independent.
Yeah, for which they're independent. So there should be procedure of searching for W. I'm wondering what is that? Not only they said subset. I've selected subset. I have X, so I have Z, and I have Y. What happens next? That's what I'm trying to understand. And I see hypothetical equation there, but how do they solve it?
There was no mention of that in the paper, so how they specifically check the gene condition.
How they compute if a gene condition is satisfied? How do they actually compute it, like the procedure?
Is that maybe in the original paper? Because this is work. So the first paper is on just the observed variables and if the gene condition holds between observed variables. Is it maybe like the original paper they talk about how you solve that efficiently?
I mean, not even efficiently, but yeah, I get it. I need to find. Okay. So it seems like the conditions are restrictive, right? Has to have twice like this 2 twice number of variables. This one is kind of interesting, but I think it has to do with something still minimality, because there could be multiple latent causes that, causing the same variables indefinitely, like one on top of another. Say L1 causes X1 and X2, L2 causes X1 and X2, X3 causes X1 and X2, and to infinity. They all could be causing X1 and X2.
So no, the number of them has to be at least at most half of the cluster.
Yeah. They're artificially said that, in order to have some minimality bound, like don't take more than certain number of latents.
And if there's, as you said, these variables have overlappings, they will check if the cluster have overlaps, and they will merge them as a new cluster.
What is an overlap?
Overlap means, for example, here, if we have, if we consider that x1, 2, 3 is a cluster and x2, 3, 4 is a cluster, these two sets have some overlaps on x2 and 3, and they will merge this cluster as a 1, 2, 3, 4 cluster.
So in the original, like in the earlier paper, the one before this one, they talk about
Can you tell me which one is that?
Yeah, I put it in the chat. It's called direct LiNGLAM. It's by Hivarinen.
So they do the gene condition.
Yeah, I think yeah, and so they talk about doing the ICA LiNGLAM algorithm too.
But ICA LiNGLAM was 2006 paper, right?
I think it's 2011, this one.
Yes, this one 2011, but LiNGLAM is 2006. So
no, true. But this one is the one I think they talk about when they. This is the one they reference when they talk about the when they talk about doing the gin condition. Like the lemma they use to define that Z is independent from Y, that lemma comes from the paper I just sent in the chat. They changed the lemma from the paper I just sent in the chat to create the Y as independent from Z. And here they say lemma in Shimizu, which is the one I just sent, considers a case where Z is a single variable and shows that Z, Y satisfies the independent noise condition if and only if Z is an exogenous or root variable relative to Y, based on which one can identify the causal relationship between Y and Z. So it should be in the paper I sent. They should talk about how they solved that problem, I think.
Yeah, I'm looking at the 2011 paper. Just okay, it would be interesting to know how this gene condition is operationalized. Like, how do you actually execute it? Well, the 2011 paper just talks about regression. Which this talk about covariance matrix kind of implies, right? So we're only looking at the second order. Well, yeah, I will need to read that other paper to understand what they're doing. So Sajad, you're like, another question. If no one has questions, I'm happy to shut up if there are others. But you're talking about this still two times dimension of latents, each whatever number of latents, they should, if they are causally related, they should be causing, or no. If they're causing the same things, I don't even know how to formulate that. But basically, the number of observed variables cannot be caused simultaneously, but more than half by more than half of the latents. So if we have k variables
in the whole the general case, like you mean the considering just x and l, could l be more than half of x? I think yeah, if that's the question.
No. Simultaneously causing that simultaneously caused by half, right? And that's
I think in the example they had L1 and L2. They both were the latent variables that caused X1, X2, X3, X4. So I guess L1 is 2 and L1 is 1 and L2 is 1, and then together they're half the total number of variables. I think in the graph you showed, Sajad, you have simultaneous cause for L1 and L2 of the observed variables X1, X2, X3, X4. That, at least that's why, yeah, here.
Yeah, in the assumption they didn't talk about one specific latent variable. They talked about a set of latent variables.
Okay.
So
but is this what you mean? Because this is also what I was confused about at first.
So L1 and L2 are related. L1 and L2, yes.
They're simultaneous cause, right?
Well, they're simultaneous cause of the X1, X2, blah, 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 up to X4. So we have 4 variables. Their assumption is we cannot have more than 4 over 2, basically, simultaneous causes. And my question is, I didn't even get to that question. My question is why? How do they use that assumption? It's a construct, right? They constructed it for a reason. Do you know why, like how they use it? Besides the minimality to limit the number of latents. Why is it 2? Why is it not 3, whatever, square root of n or something? Is there like some reason for that? I just don't know.
I think they use that in this part where they want to learn the causal order. So basically
so it's back to that theorem from 2011 paper, Shimizu.
So here they use half of one cluster and the rest of the half with the other cluster. So I think this is where they need to have at least twice the number. And also in the paper, they had like 12 pages of proof for each of them. I didn't completely go through the proof. Maybe there's some clues in there.
Okay, so we don't know, like to really understand this paper, we don't know how gene works operationally, or maybe, I mean, not to really understand, but at least to have some sense.
Implementation details. Okay.
Well, this is not details because maybe gene is another NP-hard algorithm or exponentially. It's like, yeah, how it works. But details is the proofs, right? Those are, yeah. But it's just, I think it would be good to get the gene, and I can't get it so quickly from that other paper. But because that's interesting, right? On LiNGLAM, we run ICA, and ICA gave us the independent noises for each source. And then we could do all the tests because we know if I explained it before. We know if the mixture contains that noise, then the noise source is upstream for the mixture. It has to be independent with the decomposed noise. But what they do here, well, like ICA was essential for the previous method because we needed to extract those intrinsic noises of each random variable, independent of others. And here I just, yeah. I didn't see. Besides the discrete math, let's look at all subsets. But it's interesting to see how they do it. I assume everyone understands what they're trying to do, but how they do it is.
They talk about.
Go ahead.
They talk about computational complexity of finding the independence in 3.3 computational complexity.
Which paper?
In the 2011 paper.
Yeah,
and it's a very high complexity. It's page
yeah,
1,
I'm looking
2, 3,
at
4.
It. It's like quadratic, no, cubic and
right, it's like
quadric, whatever. But what is P? Number of variables?
Number of variables.
It depends on N, P, and M.
Yeah. Where M is the maximal rank found by the low rank decomposition. Which I think talks about finding W, right? Because that's a low rank decomposition. The W for the independence between Y and Z.
So we have Z equals A times Y. We don't know A, the same as an ICA, but we know L, we know Y, and we know Z. So we need to find such transformation that is factorable into W, such that there is W as well. It's not just they're equal through that transformation that we're looking for, but also there is a W such that W transpose times A is 0, or identity rather. Okay, that's interesting how they do it. But overall, I think it's a nice choice of a paper. How did you pick it, Sajad?
I attended a number of talks on NIPS where basically I was interested in which one that was related to causal learning, because I'm new to the field and I wanted to just get a feel. And I thought this one was the most interesting one.
Yeah, it's I found it cool. And do you have any other questions? Where it looks like we're early today.
I was thinking actually how, if you look at the complexity, it would be cool to find an efficient GPU implementation for this paper, because I think that's not a very easy bone to pick, because the sort of the things they talk about are kind of smaller problems, and if we would apply this to MRI, we'd probably have to write our own sort of GPU implementation, because I can imagine that, for example, finding independence between Y and Z, if you could do that on each thread, you could do a lot of sets you could compare a lot of sets at the same time, and then in shared memory, say, okay, I found the good set, and just sort of, there's a lot of, I don't know. That's what I was thinking when I saw this. I was like, oh, I feel like this needs to be followed up by a way to implement this efficiently for large problems, which is not trivial at all. There's a lot of things and tricks you could do with CUDA to improve the algorithm here, because I feel like they didn't really do this on the GPU, probably just on the CPU for small problems, and then it works pretty okay. But if you scale this, you need to go and look at how you efficiently use your GPU. I don't know if that's right.
Yeah. I don't think they care about GPU implementation or anything. They're more about theory. But yes, exactly. To get it work, it has to be much more efficient than their numbers. Yeah, and it's parallelizable. As I totally agree. All of the tests can be done in parallel.
I think it can be solved with answer set programming approach.
You have to do the tests, though. The answer set programming can make sense of the tests. After the tests are done.
Because it occurs to me that instead of finding some W that causes the gene condition, we can just have a constraint on that. Just automatically remove everything that's not a gene condition.
Yeah, but you have to compute it, right? So that's the problem. So like once, even for them, the second part, orientation of direction, can be done through answer set programming. But the first part, where you
finding
do the
W,
test.
yeah, whether W exists is something you have to compute through some decomposition or ICA or these squares. And that's what I was talking about. You can do on a thread. You could do each thread finds a W for a different condition. I mean, it would still take a lot of time because it's not the most efficient thing to do on a thread because it just has a multiplier and an accumulate, but still.
Oh, I think you know about CUDA programming more than I do, so maybe we should do something there.
Yeah, no, I actually think it's really cool. Where we had a course where we had to implement a full deep learning thing in C on CUDA. You had to do like all these full neural network, and that was it's pretty hard to actually do.
Well, you know about this graph processors that are coming, right? Supposedly, we'll see that are sort of they're not a collection of shaders. They're specifically for matrix multiplication operations done in hardware. So hopefully, it will be easier to think in hardware once they do that. So, okay. Thanks, Sajad. Thanks, everyone. If we don't have any more questions, I think the next one is 12, and we'll continue in the sort of causal series. Benjamin, who is not here today, he will present some material from a keynote lecture from NeurIPS as well on causality. And yeah, we'll see. Then we'll come back to the safe world of matrix multiplication and linear algebra. I mean, deep learning. Yeah, so thanks.